Вы доски выровняли, чтобы было?
Ну, относительно.
Вот. Да, можете три доски ваши.
Сейчас.
Так, вы на той не пишете, да?
На
которую
той
не видно.
Да.
Вот тут
Ну, кусочек чуть-чуть не виден. Да. Угу. Ну, звук должен быть, судя по этой картинке. Здравствуйте. Идет трансляция?
Ребят, кто-нибудь может зайти на YouTube, должна трансляция или нет? У меня как грузится.
Идет
Да.
Спасибо.
Хорошо. Okay, so today we start new chapter. Chapter 2, the basics of modules. And the first section, 2.1, I'm going to call operations on modules. So first of course, I assume that you already know what the module over a commutative ring or any ring is. So we assume that you also know the isomorphism theorems. That not isomorphism theorems are known. If you don't know how to prove those theorems, it's not a problem. We're going to discuss this on a seminar on Friday. But these four theorems I'm going to use without any explanation. So the first, this is again not isomorphism theorems. So the first theorem, of course, tells us that if you have a ring of modules, say M to N, then this implies that the image of the map F is isomorphic to the quotient module M modulo the kernel of F. This is the first isomorphism theorem. The second isomorphism theorem, well, that depends what you want to call second or third. Let's choose numbering in such a way that the second isomorphism theorem is about three modules, where L is submodule in the N is a submodule in the M, and then you can consider the quotient, so M modulo L, and then you can take the quotient of the N modulo L. If you consider kind of this double quotient, this is isomorphic to the M modulo N. Now, the third isomorphism theorem, again, you can take a couple of modules, N and L, in the module M. So then you can take, first of all, take the sum of two modules and take a quotient say by the second module or by the first, doesn't really matter, the statement will be equivalent. So whenever we consider such a quotient, this is the same thing as n, and then we take the quotient by the intersection. And the last isomorphism theorem, also called the correspondence theorem, it tells us the following, that if you have a submodule then there is a bijection between submodules of the quotient module m modulo n and submodules of the module m containing the given submodule m. Okay, so this is just some very basics of the modules. I hope you've seen something like this, maybe at an exercises in your core algebra course. But yeah, of course, going to operations on the modules, of course we have the following operations. If you have a family of submodules, now parameterized by any set, so if this is a family of submodules of some module m, then of course you can define the intersection and you can define the sum. These are submodules.
Why is S is element of M?
Sorry, that's just a mistake. So the intersection is just intersection of sets, of course. You can check that if you take the intersection, this will be a module again. And the sum, if this is an infinite sum of some cardinality, of course, by definition, elements here are finite sums. In exactly the same way as we discussed last time for the ideals. There's no way in general, if you don't have any topology, to define what's the meaning of the infinite sum. Okay. Now, of course, if you compare this with the ideals, for ideals we also have the finite products. Of course, for modules it doesn't make sense to talk about finite products, but at least we have operation, so maybe this is a new operation, that the product of an ideal and a module. So if I in the ring is an ideal, and M is an R module, then we can define the product of this ideal and the module, IM. And by definition, this is again the set of all finite sums, say xi, mi, I is running between 1 and n, such that, of course, xi are all elements in the ideal, and mi are all elements in the module. Okay. Now, next definition. Now I assume that I have a family of submodules as before. So ms parameterized by some set S is a family of submodules. No, I don't want family of submodules, I just want a family of modules. They don't have to be inside some large module, just any family of modules are modules. So then for this family of modules I can define two objects, the direct sum and the direct product. So the first part of the definition, the direct product. So say this is product over little s and the capital S, and by definition this is just the set of all infinite vectors of the cardinality, of course, equal to the cardinality of the set S. So this is vectors such that component ms sits in the module ms. For example, have a finite family of modules. This will be just the vectors, and components of these vectors will be exactly elements of the module, but you can do this for any cardinality actually. And the direct sum of this family of modules, well, this is again the same vector. Again, all the components ms in the ms, module ms, and also we have a condition that these components ms are equal to 0, except maybe finitely many elements. So here in the product all the components would be non-zero, but in the direct sum they all equal to 0 except maybe finitely many. So this is the difference. And of course you can say that the direct sum always sits inside the direct product, and clearly they coincide if the set S is a finite set.
Is it like equivalent to the fact of being finite? Saying there's no, I mean, say that all the modules are non-zero, and then it would be equivalent to saying that the family S is finite, saying that the product is equal to some.
I think it's equivalent. Okay. Notice, of course, that all these statements has nothing to do with the commutativity of the ring. This all works over any ring. Now for the product we have canonical maps, the projection maps, let's call them IK. So this is a map from the product of some modules back to the module MK, and the definition is quite straightforward. You take this vector with infinitely many components potentially, and you just send this vector to one particular component with the index k, which is the same as the name of this projection. So these are projections. And using these projections we can formulate and prove the universal property of the product. So let's call this the universal property of the product. And it tells us the following, that we have the isomorphism. So let's say that for any R module L, there is the following isomorphism. You can compute home between L and the product of the modules, right? So suppose you have such homomorphism of modules, then you can compose this homomorphism with projections. So this gives you a family of the homomorphisms from L to the MK. So projections give you the canonical map to the product of the homes between L and let's say maybe again S. No, I don't know. Doesn't matter what index I use here. So again K, and K is in the same set S. And I claim that actually this canonical map, which is just a composition with the projections, is an isomorphism. Well, the proof is not easy. It's essentially you just need to look at an element on the right, so this element in this infinite product, or potentially infinite product. So suppose you have kind of infinite vector of the alpha k, right? So this is in the product of the homes. So equivalently, you can say that alpha k is a map from the L to the mk. And you want to construct a map from the L to the product, well, such that composed with the projection, it gives you exactly the map you started with. So exactly this vector of maps you started with. Now I claim you can take the following. So alpha, let's say set alpha to be a map from the L to the product, and this alpha, so I want to define how we can compute alpha on the element L, where L sits in the capital L. And this has to be, as a result, this has to be a vector with infinitely many components potentially of the L, and components are elements of the MS. So let's take this by definition to be the vector of the alpha S applied to the L. Right? So if I have any element, I can compute the corresponding map on this element. This will be an element in the MS, and from this mk in this here. But if I form an infinite vector, this is exactly something in the product. And now, of course, if you consider a map alpha, so for any L in the L, if I consider this map alpha and then I take a composition, say with the pk, well, then clearly I'll get just the given map alpha k. So we actually constructed the map in the other direction. Starting from the element here, we constructed alpha in the left-hand side. And that's the end of the proof. Now, of course, you have a dual construction. So for the direct sum, you have the injection map, and this injection map is just embeds. Okay, so say mk is sent to the vector with zeros everywhere except kth position, where we put mk. And using these canonical injections, we can formulate and prove the dual statement, the universal property of the sum. Again, this is for any module. So for any R modulo n, the home between the sum of the modules and the modulo m. If you use the injections, so you can take a home between these two modules, precompose with the injection, and then you get the family of maps, again potentially infinite family of the homes ms between ms and n. Notice I don't have a sum here, we have a product here. And of course the statement is this is actually an isomorphism. The proof is almost the same, kind of dual, so I leave this as an exercise. Well, there's no reason to expect that you have here direct sum.
But because is finite family. Because is finite family.
No, it's not finite. If this is a finite, if for a finite set S this is true, and that part also will be true. But in general, these are two different statements. Well, if you just take any map of this form and you precompose this in all possible injections, there is no reason to expect that all these injections except finitely many are zero. So this is why we have product, not a sum here. Okay, so essentially that's all I want to say about the basics of the operations. Now I also want to say something about kind of basic definitions. So about the generating sets, bases, and all that stuff. So if you can write your module as the sum of cyclic submodules, so let me be, this will be definition with many parts, so this is the first part of the definition. So then this family of elements are called elements, or the family of elements, so elements are called generators. Of the module M, or M is generated by these elements. Now, the second part of the definition is that linearly independent generators are called bases. By the way, give me an example of a module which is, say, generated maybe by one element, and this element is not a basis. So give me an example of a module for simplicity just with one generator, but this generator doesn't form a basis with one element.
Maybe.
No, zero is never a generator. So
Z quotient by n.
Will be very interesting. That quotient by what?
By some real n.
Yeah, that's an example.
Because one generated and n is independent.
So the example is the following. Right, so if I want to say that this M is generated by something, or I can say that the element that I want to consider is the class of 1, right? So this is this thing. So this is a generator. So this generator of the module M. But of course this is not a basis, because for basis we need the generator is linearly independent. This one generator is not linearly independent, because if I multiply this on the M, I'll get 0. So this is an example of a generator which is not a basis. And that is why, actually the main reason why modules theory is much more interesting than the linear algebra, because you have modules which can be maybe finitely generated, it would be analog of finite dimensional vector spaces, but there are also relations between these generators. It's not possible to choose a basis. Well, for example, here we can choose the basis. It's just not possible. So we need to keep track of the generators and the relations between generators, and maybe relations between relations, and so on. So let's continue our series of definitions. So now we have generators, we have a basis. Well, 3, a module, is called free. If it has a basis. So in this case, there is a special notation for this. For a free module, people write something like R, and then you use S in the parentheses as a power. So this is by definition a direct sum, like this. So as many copies of the ring as you have elements in your basis. So notice again, if you go back to the definition of the direct sum, here you have only finite sums, right? And if you remember the definition of the basis from linear algebra for infinite dimensional vector spaces, then basis may be infinite, but any vector is supposed to be presented as a finite sum. So this is, you can see this in this notation. Notice, by the way, that I put this S in the parentheses, because if I remove this parenthesis, this will be the product, not the sum. So for the sum, we have this additional notation.
So this is like the big S or the small s? I mean, they would put the set of indices into the parentheses?
This is big S, this is the set. And this is the little s. Like in the set theory, if you raise one set to the power of another set, you consider all the functions. Here you kind of don't want to consider all the functions, because all the functions give you products, but here you want functions with finite support. And for this, to say that, or to introduce this into notation, that we have only functions with finite support, we add this pair of parentheses. Okay, so free module. By the way, notice, so remark in the middle of the definition, any module is a quotient of a free module. Okay, part 4. A module is called finite. Also, this is the same thing as finitely generated. Well, there are two ways to formulate the definition. For example, you can say that you have finite family of generators. It has a finite set of generators, or equivalently, you can say that this is a quotient, or it is a quotient of a finite free module Rn.
Excuse me, and if we have the remarks that any model is a quotient of free model, the product model is a quotient of which kind of free model?
The product module?
Okay, the product model is some model, and it is a quotient of some free model. And what's cardinality for the indexes we must have?
You mean the product of the rings, maybe? Or what's the question? If you want to consider any product like this,
yes.
well,
I think you should take the cardinality of the family of indices just the cardinality of the product of the modules.
well, yeah, definitely. It will be just some huge cardinality. Oh, it is definitely generated by something. Well, any module is generated by something. At least you can take, for example, all non-zero elements. This will be a set of generators always. And then you can just generate a free module, but any set of generators. So. Okay, so we defined finitely generated modules. And yeah, so if you want to write this in terms of some formulas, you can say that M is finite, meaning that M is the quotient of the free module modulo some submodule. Now, last part of the definition, a module is called cyclic if it is generated by one element. Exactly as for cyclic groups. So in other words, if this is generated by one element, you have a surjective map from the ring to your module. This map has some kernel, which is an ideal. So you can say that M is cyclic if and only if M is the quotient of the ring by some ideal. And this ideal being just the kernel of the canonical map that stands 1 in the ring to the generator of the module. So example that we discussed on this whiteboard before, that was an example of a cyclic module. It was generated by one element. Okay, next definition. So M is an R module, and M is an element in this module. So the annihilator of the element M is just by definition all elements in the ring such that the product of R and M is equal to 0. So all the elements in the ring that sends M to the 0. Of course, this is an ideal. Because clearly this, if you know this property for two elements, this is true for the sum. If you multiply this identity by element in the ring, it's still true. So this is an ideal. So this is an annihilator of only one element. Now we can define annihilator of the whole module. So the definition is almost the same. So this all elements in the ring R such that Rm is equal to 0. But now this has to be true for any M in the M.
for each M.
Yeah, but you can do even better. You can say that the annihilator of the module, this is the intersection of the annihilators of elements, and M belongs to the set of generators. So, for example, for finitely generate modules, this you can present this as a finite intersection. And finally, the last part of this definition is that the module is called faithful if the annihilator is 0. So there are no elements of the ring that acts as zeros on this module, then the module is called faithful. Oh, otherwise, if this is not faithful and you, for some reasons, want to work with the faithful module, you just can take the quotient of the ring by the annihilator of the module. So annihilator acts as 0 on the module, so if you have R module M, then in fact this is a module with this ring. And this is faithful module with this ring. Okay, so
How do you say faithful in Russian? How do you translate faithful in Russian in this case?
faithful, точный. Okay. Now this finishes this section about the terminology and essential definitions. So the next section is Nakayama's lemma. So one of important and elementary statements in commutative algebra. But again, I start with the definition. Definition of the radical of a module. So M is an R module. The radical of M, so again notation rad of M, this is the intersection of all maximal ideals such that the annihilator of this module sits inside this maximal ideal. If you know some general ring theory, not necessarily commutative, that might be a surprising definition. This is not how radical of a module defined for non-commutative rings. But this is one of the kind of standard definitions in commutative algebra. You're going to see why this is a useful definition in several minutes when we prove some theorems with this definition. Okay, and maybe let's start immediately with some useful observations about this. So proposition, if you take element x in the radical of the module, then 1 minus x is invertible on the module M. Exactly as for Jacobson radical and elements of the ring. Well, we have a canonical surjection from the ring to the quotient of the ring. Let's call this R bar, and this is quotient of the R by the annihilator of the module M.
Excuse me, what does it mean y minus x is invertible on M?
Well, this is some endomorphism, right? This is a map from M to M.
Yes.
As endomorphism, this is invertible. Okay, so let's consider this canonical projection. Well, then by the correspondence theorem and the fact that x is in the radical of M, we can say that the x by this canonical surjection is sent to the element in the, well, okay, maybe let me better write, pi of x belongs to the Jacobson radical of the R bar. So 1 minus the pi of x.
How maximal ideals or just all ideals is containing?
No, this is maximal. I think I said that this is maximal, but and M is also in the spec M of R. This is some analog of the Jacobson radical, but for module. Okay, so we know that this, because this is in the Jacobson radical of the ring, so 1 minus this element is invertible in this ring, and ring being R bar. So there is element Y in the ring R, such that if you consider a product of the Y and 1 minus X, you'll get 1, well, modular the annihilator of the module. Right? If you just write the definition what it means to be invertible in the quotient ring, well, you get this definition. The product is 1 modular the annihilator. But now if you look at this identity as the identity for endomorphisms of the module M, well, everything that is in the annihilator doesn't act, so it's 0 as an endomorphism. So you'll get what you want. You constructed another endomorphism, which is that multiplication on the Y, such that the product is the identity in the ring of endomorphisms. Okay. From this observation, we can derive a corollary, which is called the Nakayama's lemma. And this is the following statement. If M is finite, you take ideal in the radical of M, and you know that submodule IM is the same as the module M. So then, in fact, your module is a zero module. Proof? Well, I know that M is finite, so let M1 Mn be the minimal set of generators of the module M. So take the set of generators as small as possible. If you have only finitely many generators, this is always possible, so to choose a minimal set. This is actually one of the main invariants of any module, the minimum number of generators. There's a kind of standard notation for this. This is called mu of n usually. Okay, so we have this minimal set.
Definition of the radical. Can I ask about the definition of the radical?
Okay.
We can consider any ideal of a ring as a module, yeah?
Mm-hmm.
And these would be kind of different, like radical of...
Oh, then you need to understand the annihilator of this ideal.
What?
You need to understand the annihilator of an ideal if you want to apply this to the ideal.
Well, I feel like radical of the ideal would be equal to a radical of the module R quotient I, R quotient the ideal. Would that be true?
No, I think if you want to relate this, well, for example, you can consider the radical of the quotient by the ideal, right?
Yeah, I'm saying it should be equal to.
And then of course the annihilator of this quotient is exactly I, so this will be something of this sort.
So they don't have anything in common, like radicals of ideals and radicals of modules, even though ideals can be viewed as modules.
No, not really, because here, for example, the main reason that this is maximum, we have only maximal ideals. So these radicals, you can, it's kind of, if you want to call this full name, you can call this the Jacobson radical of the module.
Okay, I see. Thanks.
Okay, so let's choose the minimal set of generators of this finite module. Okay, but then let's look at this identity. It means that I can take any element in the module and present this element as a finite sum of the products, where element is in the ideal and the second element is in the module. So for example, so let's say that IM is equal to M implies that I can take any element. I want to take M1, the first in the set of generators, first element on the list of generators, M1, and I can present this as a sum of some xi, mi, say I is running between 1 and n. Right? So this is some element in the M. All such elements are presented as finite sums of this form. Or I can rewrite this a little bit. I can say that 1 minus x1 applied to m1 is sum of the I between 2 and n. But now all these xi's are of course in the I. But now if I look at the xi, this is x1. x1 is an element in this ideal, which is inside the radical. So on the module, this is invertible. So this thing is invertible on the module. So it means that I can say that M1 is in the module generated by the generators starting with the second generator. And that's a contradiction because this was the minimal set of generators. And in fact I can use even smaller set of generators. So this is the end of the proof. Okay. Next, from this Nakayama Slimmer, we can derive another version of the Nakayama Slimmer, which is maybe more useful for applications. So I continue to assume that ideal I is in the radical of the module M. Now N is a submodule such that the quotient is finite, and I assume that n plus im is equal to m. So then n is equal to m. So of course we want somehow to reduce everything to the first statement. Well, first of all, we can look at the given identity and take a quotient by the n. Right? Then we can apply I think this is the third isomorphism theorem, so when you take a quotient of the sum. So this will be the same thing as the IM take a quotient by the intersection. Okay. On the other hand, if I consider module IM, I have a canonical map to the I applied to the quotient of the m by n. Well, the definition of this map is the following. If you have a finite sum, xi mi, then you just send this to the finite sum xi and then the class of mi. Right? So clearly this is a well-defined canonical map, and clearly this is a surjective map. Now what's the kernel of this map? So let's call this maybe phi. So what's the kernel of phi?
IN maybe?
No, you want this sum? You want this sum to be equal to 0, right? Of course, this is the same thing as the sum xi mi plus n.
No, it is intersection of IM and N.
Yeah, exactly this module. So it means that the sum that we consider is an element in the module M to get 0. So this is IM intersect with N. So by the first isomorphism theorem, if you know that this is surjective, so image of phi is I M N, we can conclude that IM modulo IM intersect with the N is isomorphic to the I times the quotient modulo M modulo N. So what we proved is that I M modulo N is the same as Mn. So we only need to show one thing. Remember that here we have ideal I in the radical of the module. So now of course we want to avoid this situation where our module is this quotient, but the ideal I is in the radical of M. So what we need to do? Well, okay, maybe I just tell you the last step. Since if we have ideal I in the radical of the module, and the radical always sits in the radical of the quotient. Is it clear why the radical of a module always sits in the radical of the quotient? Well, we can just look at the annihilators. If something annihilates the module, it annihilates any quotient. So they have such embedding for the annihilators, and if this is true for ideals, if you start taking intersection for take intersection for maximal ideals containing this one ideal is embedded into the other, you get the corresponding embedding for the intersections. So we proved this. Okay. So in fact, Nakayama Slimmer have a little bit more general form, more detailed form, but to prove this more general form, we need to apply the. By the way, another remark: Nakayama Slimmer and all this observation, of course, works for non-commutative rings. So if you look at the definition, at the proof, how we proved Nakayama Slimmer, this makes sense over any ring, not necessarily commutative. But the next version is going to use the little bit of determinants, and determinants usually works nicely only over commutative rings. So let's recall the Kelly-Hamilton theorem. It says the following, that if M is a finite module, suppose that its M is generated by some elements which we're going to call M, And let's take phi to be endomorphism of this module M. And set, when I apply phi to the Mi, so I can decompose this again with respect to the given set of generators. So this will be some element A with the index j and I, Mj. So in other words, I just defined the matrix associated with this endomorphism. This is the usual way to do it.
Excuse me, do you mean finite is finitely generated or free?
Finite is finitely generated. Not necessarily free, no.
What is
A?
A-I-J?
Well, you take a element in the module, you apply endomorphism, this will be another element in the module. You can decompose this using the same set of generators. So I'm doing this. And the J is just, well, these are elements of the ring. Some elements of the ring, and because I start with some element Mi, towards the answer depends on the index I. So this is just a standard linear algebra definition how you associate a matrix with any endomorphism. Okay. So then, the Kelly-Hamilton theorem tells us that if you consider the characteristic polynomial of this matrix and evaluate this characteristic polynomial on the endomorphism phi, you will get 0 and the ring in the ring of the endomorphisms. So where the characteristic polynomial has the standard definition for any matrix, that the P A of T, this is just the determinant of the T times the identity matrix minus matrix A. You definitely know this statement from the linear algebra, maybe not in such generality, maybe not for any finite module over any commutative ring. So for this statement it's important that the ring is commutative. Well, here is the standard proof. You consider, say, matrix delta or operator delta, which is just the Kronecker delta Ji times the given endomorphism phi, and then you subtract the given matrix, well, the matrix that we associate with the given endomorphism. So is a matrix with coefficients in the polynomial ring in the variable phi, which sits inside the non-commutative ring of all endomorphisms. Now let's take, so in other words, you can think about this delta as a map from the M to the N back to the M to the N. Now let's take X to be the vector of the all generators. If you apply this matrix delta to the X, you clearly get 0 just by the definition of the matrix. Now let's use some properties of the determinants. If you consider, say, another matrix, gamma, what the so-called adjugate matrix of the delta, remember that the main property of the gamma and delta is that this will be the determinant of the delta. So take this identity, apply gamma to it, so get gamma delta x is equal to 0. Product of the gamma and delta is the same thing as the, so this will be the same thing as the determinant of the delta applied to x, which is still 0. But the determinant of delta is exactly the characteristic polynomial So we see that the characteristic polynomial evaluated on the endomorphism phi is 0 applied to any of the generators. So this is a 0 endomorphism. Okay, now we have the following theorem. I'm going to call this the generalized Nakayama Slimmer. So M is a finite module. And I is any ideal. Then the following are equivalent. So the first property is that there is X in this ideal such that 1 minus X acts as 0 on this module M. So the second property is that ideal plus the annihilator of the module is equal to 0. And the third property is that Im is equal to M. So all these three properties are equivalent. Okay. So we're going to go in circle. We're going from 1 to 2, from 2 to 3, from 3 to 1. 1 to 2. Do I really need to prove anything here? Because it is given to me that X is in the ideal, and 1 minus X is an annihilator of the M. So the second line is given already. X is here, 1 minus X is here. Sorry, the statement is not correct. So this is equal to the R. Yeah, so ideal plus the annihilator of the module is as huge as possible. So then I have X in the ideal, 1 minus X in the annihilator, so then everything works. So this 1 to 2 is clear. Okay, now let's go 2 to 3. So we know that I plus the annihilator is the whole ring. How we can show that Im is equal to M?
Well, we know that an annihilator of M times M is equal to 0. Therefore, and we know that
Sorry, what annihilator is equal?
Well, annihilator of M is an ideal. Therefore, we can multiply it by the module, and we know that the annihilator of M times M is equal to 0. Yeah.
I didn't get this, so I need to.
I mean, annihilator is an ideal. Therefore, we can multiply it by the module M, right?
Annihilator is an ideal, yes. So then what?
So therefore, we can multiply it by the module M.
Multiply this part.
Well, we get.
Yes, I think.
I'm saying that if we multiply this ideal by module, we get 0 against the module, right?
Are you saying that this part and this part belongs to the annihilator of the module?
No, I'm saying that if I just take this ideal annihilator and multiply it by M, we get 0 module.
Yes.
So, and I'll also say that if we take the ring R, as an ideal of the ring R and multiply it by M, we get the whole module.
Mm-hmm.
Therefore, we didn't prove the distributivity of the...
You essentially just want to take the left-hand side and right-hand side and consider the products of the left-hand side and right-hand side with the module. Yes, you can do this. So if this is true, then this is also true, right? But this is exactly the same thing as M, and because the product of the analyte and the module is 0, so this is the same thing as IM. Okay, so actually 2 to 3 also relatively easy. So probably the non-trivial part of the statement is how you can go from 3 to 1. So any ideas how to go from 3 to 1? So we need to find X with such properties.
Yes, that's the place where we need to use the finiteness of the.
Yep, that's exactly true. Or you need to use the previous theorem. Because if you have IM is equal to M, you can look at the identity map. And the identity map has a matrix with elements in the ideal I.
Which says that phi is identity.
Yeah, so we can take phi to be the identity on the module M. So then phi as a matrix with elements in the ideal I. But if you look at the characteristic polynomial, so say matrix A, of the matrix A that you compute on the phi. So we know that this will be zero endomorphism. But on the other hand, it will be t to the n, and then there will be some coefficients, maybe plus c1, t to the n minus 1, up to cn, right? So it means when you plug in phi, which is the same thing as the identity, you will get 1 plus the sum of the coefficients. So this is 1 plus the sum of all the coefficients. So you can just take x to be by definition minus the sum of the coefficients. So when you do this, you'll get exactly an element which is 1 minus x, and this is in the annihilator of the module I, of the module M. And clearly, this will be an element in the ideal. Well, because we agreed that the matrix has elements in the ideal, and all the coefficients are just polynomials in the matrix elements. Okay. Okay, probably that's all I want to say about the Nakayama Slimmer. So let's go to the next section. So the next section is actually a topic from the homological algebra, but some of the statements might be useful when you do commutative algebra. So I decided to include this kind of sketch, 2.3. I'm going to call this exact sequences. But I'm not going to prove many of the statements, so this is why this is only a sketch. So definition. A chain of modules and maps. So So like this, you have some module mi, and you have a map which we're going to call di, and this will be a map to the mi minus 1, etc. So this is a chain of modules and maps parameterized by integer numbers. So it's called complex if I apply two consecutive maps and get 0. So di composed with the di plus 1, this is equal to 0, and this is for any I. So of course, if this is the case, it means that the image of the previous map is in the kernel of the next map. So we can define the so-called homology, hi, so this is how much the image is different from the kernel. So the kernel of the di modulo the image of the di plus 1. So the complex
homology of the quotient modular.
No, this is homology of this complex.
Shouldn't it be like homology is equal to this? Or? Yes.
Oh yeah, think. Hi of the m with the bullet, this is this thing. Yes. So the complex is called exact, or sometimes for shortness people say they have exact sequence if all the homology are actually trivial, so 0 modules. So we're not going to compute any homology in this course, but notion of exactness will be important. We can derive some statements about something using that one or another sequence is exact. Or for example, what is the meaning of the exactness of this sequence?
It's monomorphism.
Yeah. So this is equivalent to the alpha is mono. Of course, we can write the dual sequence, right? So I put 0 instead here to the right hand side, and this will be equivalent to the statement that I have a epimorphic map. Okay, now maybe let's try to understand what is the meaning of the exactness of the sequence with 3 terms. It's exact. So maybe this is the first example, this is second example. Let's give the names to the maps, alpha and beta. So it means several things. First of all, alpha is mono. Then clearly, second property is that the beta is epi. And finally, the image of alpha is the same thing as the kernel of beta. I just checked the exactness at all 3 terms, right? So here the image of the 0 is 0. It's supposed to be equal to the kernel of alpha. So the kernel of alpha is 0. It means that the alpha is monomorphism. So if at this term the image of the alpha is exactly the same as the kernel of beta. And finally here the last map is 0. So the kernel is everything, and this everything has to be equal to the image of beta. So the beta is epimorphic. Okay, proposition, which is so elementary, I'm not going to even to prove this. So if you have a family of short exact sequences, by the way, this is called the short exact sequence. Or for shortness, I'm going to write just SES. So if I have a family of short exact sequences, then the product and sum of these sequences is also short exact sequences. The proof is, I would say, completely trivial. So this is elementary observation. Now, next observation is not so elementary, and I need the large blackboard to write this. I'm not going to prove this, but you can find the proof in any homological algebra textbook and many of the commutative algebra textbooks. For example, in the book by Altman and Kleiman that I recommended, definitely there is a proof of this fact. So this is the snake lemma. The snake lemma is the following statement. So in quite general form, you can say that you have one almost exact sequence. So this is exact on the right, but not necessarily on the left. And I'm going, well, maybe I call the maps on the top U bar and the V bar. So then there is another sequence, short exact, or almost exact sequence. This is exact on the left, but not necessarily on the right. And there are maps between these two sequences. So call this F bar, F, F double bar. Okay, I need to erase the name of the lemma, because the whole idea is I can take these three maps and I can consider the kernel of F, which is embedded into the M prime, so I have exactness like this, and I have a co-kernel. And I can do the same thing for F and F double prime. This is F prime, and this is F. Well, first of all, it's not hard to see that the maps induces the maps between kernels and co-kernels. So maybe I'm going to give the maps U underlined and V underlined for the bottom part of the diagram. But the non-trivial part is that there is a connecting map that connects the kernel with the co-kernel. So let's call this delta. And this is why it's called the snake lemma. It's kind of the moving of the snake between kernels to the co-kernels. So this sequence with 6 terms is exact. So these 6 terms being these 3 kernels, the connecting map, and 3 co-kernels. So moreover, if U bar is mono, then map kernel of the F bar to the kernel of the F is mono. And if V underlined is epi, then the corresponding map on the kernels is epi.
So it's just if this will be all exact.
Yeah, if you actually have, in the beginning I formulated only the minimal data necessary to get this, but if you in fact you have two short exact sequences and the map between two short exact sequences, you get the sequence of the sequence with the 6 terms, and the sequence is exact. Well, for this sequence you can add 0 on the left and 0 on the right, and the sequence still will be exact. Okay, I think I'm out of time. Yeah, definitely I'm out of time. So we continue next week.